Hello, in this lecture we'll answer on two questions. In the first question, we find out the area of this green shape that is inside square ABCD, and in the second question, we find out the area of this green shape that is inside this quarter circle AOB. So we'll start with the first question. In the drawing, we have square ABCD. This is angle PQC, that is the right angle. This is line segment PQ that equals to 2 units in its length. This is line segment QC that equals to 3 units in its length. Again, our mission is to find out the area of this green shape. So ABCD is a square, and therefore all those four angles are right angles. So I'll write it down. This is a right angle. This is also a right angle. This is a right angle. And this is a right angle. We'll define one side of this square ABCD as A. So therefore all the four sides of this square ABCD will be equal to A. So here AB, side AB of square ABCD equals to A units in its length according to our definition. This is side AD, that is also equal to A units in its length. Side DC equals to A units, and side BC of this square ABCD equals to A units in its length. We define this line segment QB as X. The length of line segment QB equals to X according to our definition. What is the length of the missing line segment AQ? From the drawing it is very easy to see that AQ equals to AB minus QB. So write it down. AQ equals to AB minus QB. So AQ equals to AB. AB is A according to our definition, minus QB. QB is X also according to our definition. So in total, AQ equals to A minus X. AQ equals to A minus X units in its length. In the next step, we define this is angle BCQ. We define this angle BCQ as alpha. We focus on this right angle QBC. In this right angle QBC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first BC angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. AB is one side of square ABCD, therefore it is absolutely a straight line. So if we focus on this side of the straight line AB at this point Q, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of AB at point Q? We have this angle that is 90 degrees minus alpha, this angle is a right angle, plus this missing angle. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to alpha. y equals alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles on this side of AB to point Q. Exactly according to rule 3. In the right triangle APQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third recent angle must be equal to 90 degrees minus alpha. According to the same rule that said that the sum of the angles in any triangle is equal to 180 degrees. In the next step, I'll copy this right triangle APQ and this right triangle QBC in the new page, and we'll prove that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles and the copies from the original drawing. So in the next step, we will prove that those two right triangles are similar to each other according to angle similarity rule. So why those two right triangles are similar to each other? This right triangle QBC, this angle equals to 90 degrees minus alpha, and this angle equals to alpha. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. So this is angle AQP. In the right triangle APQ, and it is equal to this angle, this is angle BCQ, in the right triangle QBC. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this is angle QAP in the right triangle APQ, and it is equal to this angle, this is angle QBC in the right triangle QBC. They are both equal to 90 degrees, and therefore they are equal to each other. Finally, those two angles are both equal to 90 degrees also, therefore they are equal to each other. So actually, this is angle APQ in the right triangle APQ, and it is equal to this angle, this is actually angle BQC in the right triangle QBC. They are both equal to 90 degrees one circle, therefore they are equal to each other. So I should have proved that all the triangles in this right triangle APQ are correspondingly equal to all the triangles in this right triangle QBC. Therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. The right triangle APQ is similar, this is the side of similar, to the right triangle QBC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP in the right triangle APQ over side QB in the right triangle QBC is equal to side AQ in the right triangle APQ over side BC in the right triangle QBC, and it is also equal to side PQ in the right triangle APQ over side QC in the right triangle QBC. And again, we derive that AP over QB equals to A equals to AQ over BC equals to PQ over QC. AP is the missing side, so we leave it as it is. Over QB is X, and it is equal to AQ is A minus X, over BC is A, and it is equal to PQ, that is 2, over QC, that is 3. So in total, according to equation 1, I shall find out that AP over X equals to A minus X over A equals to 2/3. Those two expressions are equal to each other, therefore we get equation 1 from those two expressions that are equal to each other. So according to equation 1, AP over X equals to 2/3. Moving on. AP over X equals to 2/3. So here we multiply this equation 1 by X, and you get that AP equals to 2/3 X. So according to equation 1, we should find out that AP equals to 2/3 X. Those two expressions are also equal to each other, so we get equation 2 from those two expressions that are equal to each other. According to equation 2, a minus X over A equals to 2/3. So I write it down. According to equation 2, a minus X over A equals to 2/3. Here we cross multiply this equation 2, and you get that 3 times A minus X equals to 2A. We'll open the brackets on this side of this equation 2, and we get that 3A minus 3X equals to 2A. Here we subtract 2A from this equation 2, and we get that 3A minus 2A is A, so A minus 3X equals to 0. Here we add 3X to this equation 2, and finally get that according to equation 2, A equals to 3X. So if we found out that according to equation 2, A equals to 3X. In the next step, I'll copy this right triangle QBC in the new page, and we'll implement the Pythagoras theorem on this right triangle QBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here this is the right triangle QBC that are coming from the original drawing. According to the Pythagoras theorem, this right triangle QBC, QC squared, that is the square of the hypotenuse, is equal to QB squared plus BC squared. So I write it down. This will be equation 3. So QC squared equals to QV squared plus BC squared. QC is 3, therefore QC squared is 3 squared, it is 9. And it is equal to QB squared. QB is x, therefore QB squared is x squared plus BC squared. BC is a, therefore BC squared is a squared. So in total, according to equation 3, we should find out that 9 equals to x squared plus a squared. This is according to equation 3, while according to equation 2, we only found out that a equals to 3x. If a equals to 3x, it means that a squared must be equal to 3x squared. Therefore, we substitute a squared in this equation 3 by 3x squared for this equation 2. We do it now, and we get that according to equation 3, equals to x squared plus a squared, and a squared according to equation 2 is 3x squared. So in total according to equation 3, we found out that 9 equals to x squared plus 3x squared. So 9 equals to 3x squared plus 3x squared. 3x squared is 9x squared. So in total, we found out that according to equation 3, 9 equals to x squared plus 9x squared is 10x squared. So 9 equals to 10x squared according to equation 3. Here we divide this equation 3 by 10. And find again that according to equation 3, x squared equals to 9 tenths. So here we take a root out of this equation. And finally we get that x equals to the square root of 9, that is 3, over square root of 10. So we found out that x equals to 3 over square root of 10 units in its length. According to equation 2, a equals to 3x. So a equals to 3 and x is 3 over square root of 10. So in total, a equals to 3 times 3, that is 9 over square root of 10. So if we found out that according to equation 2, a equals to 9 over square root of 10 units in its length. So actually, dp or dc, this is side dc of square ABCD, is equals to a, and a equals to 9 over square root of 10 units in its length. According to equation 1, AP equals to 2/3 x. AP equals to 2/3 x. So AP equals to 2/3 x, and x is 3 over square root of 10. So here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. As we cancel 3, we have here 2 over square root of 10. So in total we found out that AP equals to 2 over square root of 10 units in its length. So actually, this is side AP is equals to 2 over square root of 10 units in its length. What is the length of this 97 PD? From the drawing it is very easy to see that PD equals to AD minus AP. So write it down. PD equals to AD minus AP. So PD equals to AD, that is A. And A is 9 over square root of 10. Minus AP, and AP equals to 2 over square root of 10. So total PD equals to 9 over square root of 10 plus 2 over square root of 10, that is 7 over square root of 10 units in its length. So AP equals to 7 over square root of 10 units in its length. So write it down. Yeah. This is 97 PD is equals to 7 over square root of 10 units in its length. The next step, we join points P and C together by straight line. By joining points P and C together, there are two right triangles. The right main triangle PDC and this right triangle PQC. Our mission is to find out this green shape. This green shape consists of those two right triangles, and therefore the area of this green shape must be equal to the sum of the areas of those two right triangles that the green shape consists of. So write it down. So if we found out that the area of the green shape in total is equal to the sum of the areas of those two right triangles. This is to say it is equal to the area of the green right triangle PDC as the area of this green right triangle PQC. Again, the area of the green shape equals to the area of the right triangle PDC plus the area of the right triangle PQC, because of the fact that the green shape consists of exactly those two right triangles. Therefore, the area of the green shape must be equal to the sum of the areas of the two right triangles that it consists of. So what is the area of the right triangle PDC? The area of the right triangle PDC is equal to the base of the triangle that is PD times the height that is DC over 2. And again, the area of this right triangle PDC is equal to the base of the triangle that is PD times the height that is DC over 2, plus the area of the right triangle PQC. What is the area of this right triangle PQC? It is equal to the base of the triangle that is PQ times the height that is QC over 2. And again, the area of the right triangle PQC is equal to the base of the triangle that is PQ times the height that is QC over 2. So here PD is 7 over square root of 10 times DC. DC is A and A is 9 over square root of 10. So it is PD times DC divided by 2. Plus the area of this right triangle PQC that is equals to PQ that is 2. The base of the right triangle PQC is PQ that is 2 times the height QC that is 3 divided by 2. So there are the right triangle PQC equals to the base that is 2 times the height that is 3 divided by 2. So here, what is the value of this expression? We have here 7 times 9 is 63 over square root of 10 times square root of 10 is 10 divided by 2 plus 2 times 3 over 2. 2 over 2 is 1, so we have to only be 3. 63 over 10 over 2 equals to 63 over 2 times 10 plus 3. And 63 over 2 times 10, so 2 times 10 is 20. So total this expression equals to 63 over 20 plus 3. So here we multiply 3 by 20. We multiply 3 by 20 and then we divide it by 3 in order to a common factor with this number, and we get that in the numerator we have 63 plus 3 times 20 is 60 divided by 20. 63 plus 60 is 123 divided by 20. 123 over 20 is 6.15. So in total we found out that the area of the green shape equals to either 123 over 20 square units, or in terms of numbers it is equal to 6.15 square units. Okay, again, we actually found out that the area of this green shape equals to either 123 over 20 square units, so in terms of numbers, the area of this green shape is equal to 6.15 square units. So we finished with the first question. In the next step, I will present to you the second question and we will solve it. Our mission in the second question is to find out the area of this green shape. So in the drawing we have quarter circle AOB. Those three angles, they are all right angles. We know that OB equals to 5 units in square. That is to say, the radius of this quarter circle equals to 5 units, because OB is the radius. In addition, we know that arc AP equals to arc PQ equals to arc QB. Again, our mission is to find out the area of this green shape. So first of all, we'll join points O and P together by a straight line. And we'll join points O and Q together by a straight line. OP and OQ, they are both the radii of the circle, that is equal to 5. So it starts from the center of the circle and that's at any point on the circle itself. So this is exactly the definition of a radius. So OP is the radius R that is equal to 5, and OQ is the radius R that is also equal to 5. So here we can implement rule 20 because of the fact that arc AP equals to arc PQ and is also equal to arc QB. For that reason, we can implement here rule 20. So I repeat quickly rule 20. According to rule 20, in front of equal arcs, there are equal center angles. So in the drawing we have a circle, and we know that arc AB equals to arc CD. And because of the fact that arc AB equals to arc CD, according to this rule 20, in front of those two equal arcs, we have equal center angles. That is to say, those two center angles alpha and beta that are located in front of those two equal arcs must be also equal to each other. That is to say, center angle alpha equals to center angle beta. Okay? So whenever you have equal arcs in a circle, then the center angles that are located in front of those two equal arcs must be also equal to each other. Okay, so we're going to implement rule 20 in our drawing. Why? Because in our drawing, we know that arc AP equals to arc PQ equals to arc QB. So in front of those three equal arcs, we have equal center angles. In front of arc AP, we have this angle, center angle AOP. In front of arc PQ, we have center angle POQ. And finally, in front of arc QB, we have center angle QOB. And because of the fact that in front of equal arcs are equal center angles, it means that those three angles, three center angles AOP, POQ, and QOB that are located in front of those three equal arcs must be also equal to each other. So those three center angles are equal to each other. So if we define the size of this center angle AOP as x, then the size of this center angle POQ must be also equal to x, and the size of center angle QOB must be also equal to x because they are equal to each other according to rule 20, because they are located in front of those two equal arcs, therefore they are equal to each other. So in total, it is very easy to see that angle AOB in total equals to x plus x plus x. So angle AOB equals to 3x from one side, but from the other side, angle AOB equals to 90 degrees, and therefore 3x equals to 90 degrees. X plus x equals to 90 degrees, because angle AOB equals to 90 degrees. So I write it down. 3x equals to 90 degrees according to rule 20. Here we divide this equation by 3, and finally we get that the missing angle x equals to 90 degrees over 3, that is 30 degrees. So actually, center angle AOP is equal to x is equal to 30 degrees in its size. Center angle POQ, that is also equal to x, it is equal to 30 degrees in its size. And finally, center angle QOB, that is also equal to x, it is equal to 30 degrees in its size. So in the right angle MOP, this angle equals to 30 degrees, this angle equals to 90 degrees, and therefore this 30 angle must be equal to 60 degrees in its size. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. 60 degrees plus 30 degrees is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the right triangle NOP, this angle equals to 30 degrees plus 30 degrees, that is 90 degrees. This angle is a right angle is equal to 90 degrees, and therefore this flat angle must be equal to 30 degrees in its size. In the next step, I'll copy the right triangle MOP and this right triangle NOP. Copy the right triangle MOP and this right triangle NOQ in a new page, and we prove that those two right triangles can go into each other according to angle side angle rule. Actually, those are the two right triangles MOP and NQO that are going to the original drawing. In the next step, we will prove that those two right triangles can go into each other according to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to 60 degrees and therefore they are equal to each other. So actually, this is angle MPO. In the right triangle MOP, and it is equal to this angle that is actually angle NOQ. In the right triangle NQO. They are both equal to 60 degrees and therefore they are equal to each other. In addition, those two angles are both equal to 30 degrees, therefore they are equal to each other. So actually this is again MOP. In the right triangle MOP, and it is equal to this angle, this is actually angle NQO. In the right triangle NQO. They are both equal to 30 degrees and therefore they are equal to each other. And finally, side PO equals to side QO. They are both the area of the circle. They are equal to 5 and therefore they are equal to each other. So PO equals to QO. Is the radius of the quarter circle that is equal to 5. So actually proof that those two angles, the side that included between those two angles, that is side PO, are correspondingly equal to those two angles, and the side that included between those two angles, that is side QO, and the right angle, and QO. And therefore, we should prove that those two right angles can go into each other according to angle side angle rule. So I write it down. So triangle MOP congruent, this is the same congruent to the right triangle NQO, according to side angle side angle rule. We have two angles inside OP in this right triangle NQO that are correspondingly equal to those two angles inside OP of the right triangle MOP. Therefore, those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that they have also the same areas. Okay. That is to say, the area of this right triangle MOP equals to the area of this right triangle NQO. So I write it down. The area of the right triangle MOP is equal to the area of the right triangle NQO. Let's do it again. The two triangles that are congruent to each other, they have also the same areas. That is to say, the area of the right triangle MOP equals to the area of the right triangle NQO. This is according to equation 1, right? But what is the area of this right triangle MOP? The area of the right triangle MOP, or the right triangle MOP, consists of two components. We define this point as point S. So the right triangle MOP consists of two components. It consists of this green quadrilateral MNSP, and it also consists this right triangle NOS. And therefore, the area of this right triangle MOP must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of this green quadrilateral MNSP plus the area of this right triangle NSO. So I write it down. The area of the right triangle MOP equals to the area of the green quadrilateral MNSP plus the area of this right triangle NSO. Again, because of the fact that triangle MOP consists of two components, the area of the right triangle MOP must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of quadrilateral MNSP plus the area of the right triangle NSO. And we know that the area of triangle MOP equals to the area of triangle NQO. Okay, this is the right triangle NQO. This right triangle NQO consists of two triangles. It consists of this right triangle. It consists of this right triangle NSO, and it also consists of this triangle QSO. And therefore, the area of this right triangle NOQ must be equal to the area of the two components that it consists of. That is to say, it must be equal to the area of this right triangle NSO plus the area of this right triangle plus the area of this triangle. It is not right triangle, triangle SQO. So I write it down. The total we can find out that the area of this triangle NOQ is equal to the area of this right triangle NSO plus the area of this triangle QSO. Okay, again, we can find out that again the area of right triangle NQO must be equal to the sum of the areas of the two components it is consists of. This is to say it must be equal to the area of the right triangle NSO plus the area of triangle QSO. So this is equation 1. In this equation 1 we have the area of triangle NSO on both sides of the equation. So we subtract the area of triangle NSO from this equation, and you get that. So the area of triangle NSO will get cancelled, and we're left only with the area of quadrilateral MNSP is equal to the area of triangle SQSO. So if we found out that the area of this green quadrilateral MNSP is equal to the area of this triangle OSQ. So if we define the area of this green quadrilateral MNSP as A, then the area of this triangle OSQ must be also equal to A because they are equal to each other. Okay, our mission is to find out the area of this green shape. So what is the area of the green shape? From the formula it is very easy to see that the area of the green shape is equal to the area of this quadrilateral MNSP plus the area of this shape PQS. So repeat again, if we found out that the area of the green shape in total is equal to the area of quadrilateral MNSP plus the area of shape PQS. But we have already found out that the area of this green quadrilateral MNSP equals to the area of this triangle SQO. Therefore, we can substitute the area of this quadrilateral MNSP by the area of this triangle SQO. We do it now, and we get that the area of the green shape equals to the area of quadrilateral MNSP. The area of quadrilateral MNSP equals to the area of triangle SQO. So we substitute the area of quadrilateral MNSP by the area of triangle SQO. plus the area of shape PQS. So in total, if you found out that the area of the green shape equals to the area of triangle PQS plus the area of shape, again, the area of the green shape in total equals to the area of triangle SQO plus the area of shape PQS. So here, the area of the green shape in total equals to the area of this triangle OSQ plus the area of this shape PQS. But the area of triangle OQS plus the area of this shape, the area of this triangle OSQ plus the area of this shape PQS is equal to the area of sector POQ. You can see that sector PQO consists of this shape PQS and this triangle QOS, and therefore the sum of the areas of those two shapes, it is equal to the area of sector POQ. So sector PQO consists of two components. It consists of this shape PQS and this triangle SOQ, and therefore in total the area of sector PQO must be equal to the area of the green shape PQS plus the area of this triangle QSO. Okay, so if we found out that the area of triangle SQO plus the area of shape PQS equals to the area of sector PQO. The rounded line above PQO is the sign for a sector. This means that we are talking about sector PQO. So in total we shall find out that the area of the green shape equals to the area of sector PQO. Again, we shall find out in total that the area of the green shape equals to the area of sector PQO. Again, the area of this green shape equals to the area of this sector PQO. But what is the area of the sector PQO? Actually, the area of any sector equals to pi r squared. That is the area of the circle that contains the sector times the angle between the legs of the sector divided by 360 degrees. So the area of sector POQ must be equal to pi r squared. That is the radius, and that is the area of the circle that contains sector POQ times the angle between the legs of the sector. Sector POQ has two legs, leg PO and leg QO, and the angle between the legs of sector POQ is this angle, that is 30 degrees. So it is 30 degrees over 360 degrees. So in total we shall find out that the area of sector PQO equals to pi r squared times 30 degrees over 360 degrees. That is actually also the area of the green shape, that is the area that we are looking for in this question. We have already found out that the radius of this quarter circle r equals to 5. If r equals to 5, r squared equals to 5 squared, that is 25, so pi r squared is 25 pi. 30 degrees over 360 degrees is 1 over 12. So in total we shall find out that the area of this green shape equals to either 25 pi over 12 square units, so in terms of numbers, the area of this green shape equals to 6.545 square units. Repeat again, we shall find out that the area of this green shape equals to either 25 pi over 12 square units, so in terms of numbers, the area of this green shape equals to 6.545 square units. So we finish with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. this question, our mission is to find out the area of this green shape. In the drawing, we have square ABCD. This is angle PQC, that is the right angle. This is line 7PQ, that is equal to 2 units in its length. This is line 7QC, that is equal to 4 units in its length. Again, our mission is to find out the area of this green shape. So because of the fact that ABCD is a square, all those 4 angles are right angles, and all the sides of this square ABCD are equal to each other. We defined one side of this square as A, therefore all the 4 sides, AD equals to DC equals to CB equals to BA equals to A, according to our definition. We defined the length of this line segment QB as X. So what is the length of AQ? From the drawing it is very easy to see that AQ in total equals to AB minus QB. Again, AQ equals to AB minus QB. So AQ equals to AB, that is A, minus QB, that is X. So in total, AB equals to A minus X. We defined this angle QCB as alpha. So in the right triangle QBC, this angle equals to alpha, this angle equals to 90 degrees. And therefore this third missing angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. AB is one side of square ABCD, therefore AB is the side of a square, it is absolutely a straight line. If we focus on this side of the straight line AB, this point Q, here the sum of the angles must be equal to 180 degrees, according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of AB at point Q? We have this angle, this is 90 degrees minus alpha. This angle is a right angle plus this missing angle. In total, the sum of those 3 angles must be equal to 180 degrees according to rule 3. Therefore, this first missing angle must be equal to alpha 1, because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles on this side of AB at point Q according to rule 3. So this missing angle must be equal to alpha. So in the right triangle AQP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. In the next step, I'll copy this right triangle APQ and this right triangle QBC in a new page, and we prove that those 2 right triangles are similar to each other according to angle similarly to rule. Okay, those are the 2 right triangles, APQ and QBC, that are going from the original drawing. In the next step, we prove that those 2 right triangles are similar to each other. So why those 2 right triangles are similar to each other? First of all, those 2 angles are both equal to alpha, therefore they are equal to each other. In addition, those 2 angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those 2 angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we prove that all the 3 angles of this right triangle or AQP are correspondingly equal to all the 3 angles of this right triangle QBC, and therefore those 2 right triangles are similar to each other according to angle similar to rule. And from the fact that those 2 right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that AP over QB equals to AQ over BC equals to PQ over QC. AP is the missing side, so we need to see it is QB is X, AQ is A minus X, BC is A, PQ is 2, and QC is 3. So in total, we found out that according to equation 1, AP over X equals to A minus X over A equals to 2/3. Those 2 expressions are equal to each other, therefore we get equation 1 from those 2 expressions that are equal to each other. So according to equation 1, AP over X equals to 2/3. We multiply this equation 1 by X, and finally found out that AP equals to 2/3 X. AP equals to 2/3 X. Those 2 expressions are also equal to each other, therefore we get equation 2 from those 2 expressions that are equal to each other. So according to equation 2, A minus X over A equals to 2/3. Here A minus X over A equals to 2/3. Here we cross multiply this equation 2, And finally found out that 3 times a minus x equals to 2a. Here we open the brackets on this side of this equation, and found out that 3a minus 3x equals to 2a. Here we subtract 2a from this equation, and finally found out that 3a minus 2a is a, so a minus 3x equals to 0. Here we added 3x to this equation, equation 2, and finally found out that according to equation 2, a equals to 3x. In the next step, let's copy this right triangle QBC in the equation and implement the Pythagoras theorem on this right triangle QBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle QBC that I covered from the original domain. According to the Pythagoras theorem, in this right triangle QBC, QC squared, that is the square of the hypotenuse, equals to QB squared plus BC squared. QC is 3, therefore QC squared is 3 squared, that is 9, and it equals to QB squared. QB is x, therefore QB squared is x squared, plus BC squared. BC is a, therefore BC squared is a squared. So in total, according to equation 3, 9 equals to x squared plus a squared. But according to equation 2, we have already found out that a equals to 3x. If a equals to 3x, it means that a squared must be equal to 3x squared. Therefore, we can substitute a squared in this equation 3 by 3x squared from equation 2. We did it, and we found out that according to equation 3, 9 equals to x squared plus a squared. A squared is 3x squared according to equation 2. So in total, 9 equals to x squared plus 3x squared. So 9 equals to x squared, 3x squared is 9x squared. So in total, 9 equals to x squared plus 9x squared. X squared plus 9x squared is 10x squared. So in total actually found out that 9 equals to 10x squared. Here we divided the equation by 10, and finally found out that x squared equals to 9 times. Here we took out of this equation, equation 3, and finally found out that according to this equation, equation 3, x equals to the square root of 9, that is 3 over square root of 10. So x equals to 3 over square root of 10 units in its length. According to equation 2, a equals to 3x. So a equals to 3x, and x is 3 over square root of 10. So in total, a equals to 3 times 3, that is 9 over square root of 10. So we found out that according to equation 2, a equals to 9 over square root of 10 units in its length. That is to say, DC is equals to a equals to 9 over square root of 10 units in its length. According to equation 1, AP equals to 2/3 x. So AP equals to 2/3, and x is 3 over square root of 10. So in total, we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. So in total, we found out that AP equals to 2 over square root of 10. Again, AP equals to 2 over square root of 10 units in its length. What is the length of PD? What is the length of this line segment PD? From the domain, it is very easy to see that PD equals to AD minus AP. But again, PD equals to AD minus AP. So PD equals to AD, AD is A, and A is 9 over square root of 10 minus AP. AP is 2 over square root of 10. So in total, PD equals to 9 over square root of 10 minus 2 over square root of 10. 9 over square root of 10 minus 2 over square root of 10 is equal to 7 over square root of 10. So in total, we found out that this is line 7 PD, that is equals to 7 over square root of 10 units in its length. In the next step, we join points P and C together by side line. By joining points P and C together by side line, we get there two right triangles, the right triangle PDC and the right triangle PQC. It is very easy to see from the drawing that the green shape consists of exactly those two right triangles, and therefore the area of the green shape must be equal to the sum of the areas of the two right triangles that it consists of. That is to say, the area of the green shape must be equal to the area of this right triangle PDC plus the area of this right triangle QPC. Repeat again, the area of the green shape in total equals to the area of the right triangle PDC plus the area of the right triangle PQC. What is the area of the right triangle PDC? The area of this right triangle PDC equals to the base of the triangle that is PD times the height that is DC over 2. Okay, again, the area of the right triangle PDC equals to the base that is PD times the height that is DC over 2. What is plus the area of the right triangle PQC? What is the area of this right triangle PQC? Is equals to the base that is PQ times the height that is QC over 2. Is equal to the base that is PQ times the height that is QC over 2. PD is 7 over square root of 10, TC is 9 over square root of 10 divided by 2, plus PQ is 2, QC is 3 divided by 2. What is the value of this expression? 7 times 9 is 63, square root of 10 times square root of 10 is 10 divided by 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. In total, this expression equals to 3. So in total, we actually found out that this expression equals to 63 over 10 over 2. 63 over 10 over 2 equals to 63 over 10 times 2 plus 3. 10 times 2 is 20. So in total, this expression equals to 63 over 20 plus 3. Here we multiply 3 by 20 and then we divide it by 20 in order to become a part of this number. We found out that in total, the numerator of this expression we have 63 plus 3 times 20 that is 60 divided by 20. 63 plus 60 divided by 20. 63 plus 60 is 123 divided by 20. So we actually found out that the area of this ring shape equals to either 123 over 20 square units, or in terms of numbers, the area of this ring shape equals to 6.15 square units. We finish with the first question. In the next time, I actually presented to you the second question, and we solve the second question of this lecture. Our mission in the second question is to find out the area of this ring shape. So in the drawing, we have quarter circle A or B. Those three angles, they are all right angles. We know that OB equals to 5, that is to say the radius of this quarter circle equals to 5 units. In addition, we know that arc AP equals to arc PQ equals to arc QB. Again, our mission is to find out the area of this ring shape. So in the first step, we join points O and P together by third line. And we also join points O and Q together by third line. OP and OQ, they are both the radius of the circle, it's equal to 5 units in its length. Okay, so because of the fact that arc AP equals to arc PQ equals to arc QB, we can implement in rule 20. So repeat quickly on rule 20, going to rule 20. In front of equal arcs, there are equal central angles. So in the drawing we have a circle, and we also know that this is arc AB, that is equal in its length to this arc CD. And according to this rule 20, in front of those two equal arcs, there are equal central angles. That is to say, central angle alpha equals to central angle beta because of the fact that those two central angles are located in front of equal arcs, and therefore they must be also equal to each other. So we can actually implement rule 20 in our drawing. Right, because in our drawing, arc AP equals to arc PQ equals to arc QB. In front of arc AP, we have central angle AOP. This is central angle AOP. In front of this arc PQ, we have central angle POQ. And finally, in front of arc QB, we have central angle QOB. And because of the fact those three central angles AOP, POQ, and QOB are located in front of those three equal arcs AP, PQ, and QB, they must be also equal to each other. That is to say, central angle AOP equals to central angle POQ equals to central angle QB. So if we define the size of this central angle AOP as x, then the sides of this right triangle POQ must be also equal to x, and the sides of this right triangle QOB must be also equal to x, because they are equal to each other. So in total, the sum of those two right triangles is x plus x, that is x plus x plus x, that is 3x. But the sum of those triangles, in total, it is equal to angle AOB. And it is given in the equation that angle AOB equals to 90 degrees in its side. Therefore, 3x, this is the sum of those three central angles, must be equal to angle AOB. So 3x equals to angle AOB, that is 90 degrees. So 3x equals to 90 degrees. We divided this equation by 3 and finally found out that the missing angle x equals to 30 degrees in its sides. 90 degrees over 3 is 30 degrees. So center angle AOP equals to 30 degrees in its sides, center angle POQ equals to 30 degrees in its sides, and finally center angle QOB equals to 30 degrees in its sides, according to rule 20. In the next step, we focus on this right angle MOP. This right angle MOP, this angle equals to 30 degrees, this angle equals to 90 degrees, and therefore this first angle must be equal to 60 degrees in its sides. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we focus on the right triangle NOQ. In this right triangle NOQ, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 30 degrees in its sides. According to the sum rule that said that the sum of the angles in any triangle is equal to 180 degrees. In the next step, I copy the right triangle MPO, this right triangle NQO in a new page, and we prove that those two right triangles can go into each other according to angle side angle rule. So actually, those are the two right triangles MOP and NQO that are coming from the original drawing. So why those two right triangles can go into each other? First of all, those two angles are both equal to 60 degrees. 60 degrees, and therefore they are equal to each other. In addition, those two angles are both equal to 30 degrees, and therefore they are equal to each other. And finally, PO equals to QO, they are both the radii of the circle, therefore they are equal to each other. So we shall prove that those two angles, the side that is included between those two angles, that is side PO, are correspondingly equal to those two angles, and the side that is included between those two angles, that is side QO, and the right triangle MQO. Therefore, those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that they have also the same areas. That is to say, the area of this right triangle MPO equals to the area of this right triangle MQO. Again, the area of the right triangle MOP equals to the area of the right triangle MQO. But because of the fact that this right triangle MOP consists of two components, it consists of this quadrangle M and SP, it also consists this right triangle NSO. Therefore, the area of this triangle MOP must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of this quadrangle M and SP plus the area of this right triangle NSO. So the area of the right triangle MOP equals to the area of quadrangle M and SP plus the area of the right triangle NSO. And we have here the right triangle MOP equals to the right triangle NQO. So this is the right triangle NQO. It is very easy to see from the drawing that this right triangle NQO consists of two small triangles. Consists of this small triangle NSO, and it also consists of this triangle SQO. And therefore, the area of this triangle must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of this triangle NSO plus the area of this triangle SQO. And here, the area of triangle NQO must be equal to the sum of the two components, to the sum of the two areas of the two components that it consists of. That is to say, it must be equal to the area of the right triangle NSO plus the area of triangle SQO. So we have the right triangle NSO on both sides of the equation, so we subtract the area of the right triangle NSO from this equation 1. So the area of triangle NSO will be cancelled, and we are left only with the area of quadrilateral NSP that equals to the area of triangle QSO. So here the area of this quadrilateral NSP equals to the area of this triangle SQO. Our mission is to find out the area of this green shape. The area of this green shape equals to the area of this quadrilateral MNSP plus the area of this green shape PSQ. So again, the area of the green shape equals to the area of quadrilateral MNSP plus the area of the green shape PQS. But we have already found out that the area of quadrilateral MNSP equals to the area of triangle SQO. Therefore, we can substitute the area of this quadrilateral MNSP by the area of triangle SQO. We did it, and we found out that the area of the green shape equals to the area of quadrilateral MNSP. We substitute the area of quadrilateral MNSP by the area of triangle SQO plus the area of the green shape PQS. So in total, we found out that the area of the green shape equals to the area of this triangle SQO plus the area of this green shape PSQ. But the area of triangle SQO plus the area of the green shape PSQ equals exactly to the area of sector POQ. Okay? And therefore, the area of the green shape equals to the area of sector POQ. So the area of the green shape equals in total to the area of sector PQO, because of the fact that sector PQO consists of exactly those two components. This green shape PSQ and this triangle PQS. Okay? So in total, the area of the green shape equals to the area of sector PQO. What is the area of this sector PQO? Actually, the area of any sector equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, divided by 360 degrees. Therefore, the area of this sector POQ must be equal to pi r squared, times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. Okay, the area of sector PQO equals to pi r squared, times 30 degrees over 360 degrees. R is 5, therefore r squared is 5 squared, that is 25, so in total this expression equals to 25 pi. 30 degrees over 360 degrees is 1 over 12. So in total, we should have found out that the area of this green shape equals to either 25 pi over 12 square units, so in terms of numbers, the area of this green shape equals to 6.545 square units. Okay, thank you very much.